of the previous part of this lecture, okay? Because we have to teach in the medium part of this lecture. So that there will be an overview of the transformers, okay? So the transformers, the first thing is that the power system is characterized by different voltage. The second thing is that transformers is used to transfer the power between these different voltage levels. And so the one is the ability to change the voltage levels without very high cost. So it will be the main advantage of the one benefits to use the AC systems rather than the DC systems. And so the one that we're just to develop the model of the transformers and the wire as per unit, okay, for this lecture. So that in the idea transformers, so the three assumptions, so no real power losses, the magnetic core has infinite permeability and no leakage flux, okay. So also there will be two sides, the primary side and the secondary side of the transformers. Yeah, of course, the primary and secondary side, the two sides of the transformer. Okay, so the solution for the first homework I will send you today. Okay. So this is the relationship of the ideal transformers. So please do remember that the direction of the current and it's generated the magnetic flux. We use the right hand rulers, okay, with the right hand. The four fingers is the direction of the four fingers will be the direction of the current, and the thumb, the direction of the thumb is the direction of the magnetic flux in the core, okay. So in the ideal transformers, we will see that the voltage ratio of the between the primary and secondary between the primary side and secondary side will be the same as the ratio of the turns, okay. So also we're going to see that just showing them this, the voltage level, the ratio is the same as the ratio of the turns, okay. So the current relationship, and by steps such as these three steps, you can get these equations between the sum of the current in the two sides and with its magnetic expressions. So that we can get there will be a negative relationship between the current and the primary side, between the current in the primary side and secondary side with the ratio of the turns of these two sides, okay? So that the current in the primary side divided by the current of the secondary side is 1 divided by 8. 8 here is the ratio of the turns, okay? So the secondary side is related to the nominators here. However, the primary side is relevant to the denominators here, okay? So this is current and voltage relationships in the ideal transformers. We can just to summarize these relationships in this matrix. So V1 is the primary voltage and current. So this is green is the transfer matrix, and this is the voltage and current in the secondary side. And for the impedance transformation examples, we said we can use these equations. Okay, so we can use this transfer matrix here, and we can get that this is the primary side, the impedance in the secondary side should be mapped with the A square to get the impedance, the equivalent impedance in the first side of the transformer. Okay, so these three relationships: voltage is a positive relationship, current is a negative relationship, just like smooth down, okay? The turns, the end turns in each side, and for the impedance, it should be the secondary mapped with the A square. The A here is the ratio of the turn end of the turns, ratio of turns between these two sides, the primary and the secondary. Okay, so this is the ideal situations. And for the real transformers,
have no losses.
yeah, losses, leakage, faults, and leakage, permeabilities.
Okay.
So everything is imperfect anymore. Okay. So for there will be three types of the losses compared with the transformers in this ideal scenarios. So the first one is the real power losses. Okay. So it will be almost the whole part of the real power losses will be mated with the resistance of the resistance in the windings. Okay, so it will be related by square current mapped with the resistance. And so most of these energies in the electric powers will be transferred to the heat. Okay, so it will be very hot if you just touch this winding. And second one is the eddy current. Okay, so eddy current is resulted from the changing flux in the core, right? Because when the core is not enough, the volume of the core is not enough, so say there will be eddy. So the eddy is called that's the current runs in a circular direction. Okay, so from the beginning, one circle and end to beginning. Okay, so we could use the eddy current. So to reduce it, we can use the animation just to cut the core of the core. Yeah, slice. It is very maybe here to be 5 slices. Okay, 5 slices. The eddy current is still released in each slices or in each laminations. In each lamination, however, it will become much smaller and much smaller even than compared with 10% of this, the original eddy current. Okay, so the sum of these 5 eddy current is smaller than the original. Okay, so if the sum of these eddy current is equal or even larger, so when we should do this, let's use this, the whole part of this core will be enough. Okay, so the third one is hysteresis losses, and it's proportional to this EMH. Right? It's the magnetic field intensity to the flux loss. Okay, let's see, and here is the relationship between these two parameters. Okay, B and H. So the common side, the larger or the fatter the shape is curve is, or this area is, the larger the hysteresis losses will be. Okay, so you need to choose more suitable materials of the landings or the cores to make sure that there will be a much thinner. Okay, so everybody will prefer the thinner figure. Okay, like our transformers with this pH curves. Each will also prefer the thinner figure. And for more details, of course, in motor theory for turbine, it will tell you why it should be doing like this. Okay, so because we are considering the real transformers, so the second step we need to consider the leakage flux. So you can see that the leakage flux, the extra variables in the previous equations, the previous in the ideal environment or the ideal conditions, you want to know the exact things. Okay, so lambda is directly equal to only the main terms of this one side multiplied by phi n. Okay, so if we have a linear magnetic medium, we could just to convert this this is equal. Okay, so the lambda is proportional to the inductance multiplied with the current, the flow, voltage. Okay, so in our previous lecture we know that, and we use these two mathematic relationships to in these two equations we get this. Okay, so the voltage here, so the voltage. One thing I have to remember is that in the lowercase voltage we call it the instantaneous voltage. Okay, so some of your in the first work, that's like the first questions. So we need to know if the V is instantaneous voltage. Some this. Okay, because instantaneous, it will be a weak form. Okay? In the sinusoidal or the cosine math functions. Okay, so this uppercase V is actually maybe the effective value. Okay, just like effective value. Just like okay, so we were just to converge because this we form this AC V form is equal to just like this EC form. Okay, so this will be a constant number. This is beta is a constant number. So make sure that if you are required to calculate the instantaneous voltage or current, make sure it should be expressed by a function. Okay? Yes, of course. Like this. Here we'll simulate it to be 1. Okay? 1 volt expressions. So that for this V, it is instantaneous. So it's instantaneous voltage is not the voltage in a constant. Okay? So the constant is the equivalent to the instantaneous, but they are not the same. Okay? So the V voltage in the primary side, the current or the losses in the resistance, and for the L, because the magnetic field we know that it's being generated by change, by the variation of this, or how quick this current is changed. Okay, so it will be the differentiation of this I and the N, also the differentiation of phi n. Okay. So also the V1 and V2 can be expressed here. Okay. So in the two sides of the transformers. Okay, so we need to, these two are not equal anymore because there should be a phi m, okay, because there should be a phi m in the core, because you can see that the magnetic motive force here is no longer is zero, so there will be a phi m, the flux in the core between the primary side and secondary side, okay? So we are assuming that this is the reluctance between, or the reluctance generated by this non-zero FF, okay? So we're going to use this magnetizing current, the current here, okay? So this is flux in the core divided by the inline currents, and also the 8 primary side, or the transferred primary side, right? Primaries transfer the current in the secondary side current to the primary side. This is transferred current in the ideal conditions, and this is the radial, and this is the external losses generated by the magnetic flux, okay? So the I1, we assume that this extra losses in the real scenarios could be IM, okay? Or we could say that IM is modeled, it can be modeled by the distance and the inductance here. And in that case, we could use these trivial relationships, so we can drive a equivalent to QH models. You can see that, okay? So this would be the C, the C here, okay? The subtitle C here is means the power, okay? It does not mean the capacity or capacitors here, okay? The core, the resistance of the core, the resistance of the inductance of the XM is in the winding, okay? So this part, the winding, which is the core, okay? And for this, the R1 and the X1 is represent the impedance in the line, okay? Because of the transmission line. So everything is no longer ideal, okay? So also because for here, because we have technically we have count the resistance and reluctance of the core in the primary side, okay? So that there will be no more impedance of generated by the cores in the secondary side. So we only needed to, there is only one core here, so we only needed to calculate for ones. So for the secondary side, there will only be the impedance of the line, the transmission lines, okay? Like R2 and J2. Okay, so we can, in the next step, we need to further simplify this equivalent circuit. So we can just to use these relationships between the two sides, okay? So we can just do equivalent, we can move this part to the primary side, okay? So we'll say that the distance on the secondary side is buffered with A square, okay? The A square is, we'll say that there should be the ratio of turns, okay? So it's A. So in our previous relationship of the impedance to A square, my current, and for after we have moved here, after we have moved this impedance to the primary side, so there will be two impedance of the transmission lines, okay, here. So we can just sum them up. So we call it the RE, right? It describes express the whole part of the transmission impedance of the whole network, okay? So it includes the primary side impedance and also includes the secondary side. You can see the R1 and the transferred R2. And in the same way, so the X, the inductance, the sum of the inductance equal to the S1 and the transferred S2. Okay? So understand? So we can just do like this. Okay, so this includes the impedance or transmission impedance of both the primary sides and the secondary sides, and this is the impedance of the cores. Okay, the core between these two sides. Okay, so in our previous lecture we stopped here, right? Okay, so we're just start our forwarding. Okay, so then how to calculate the all of these parameters here? Okay, so the parameters are determined based on so net data. So do you know what is the net? What is the net?
Yeah.
Okay, that's my yeah. So this is the transformer. This is the net flash. The code is okay. So its voltage is 2 and 20 V versus the 1 and 10 volt. We know that the ratio terms will be 2. Okay. This is the net here, and every parameters in the branch is rated. Okay. And so we need two forms of the test, okay? So the open security test and the short security test. Like this, okay? Next, for the open security, you know what is the open security? You card power flow to the secondary side. When we charge, so I2, so the current in the secondary side, so it equal to what? When we charge
0.
2?
0.
0? Okay, so right. So 0. And for this part, the current here, what is the when the I2 here is 0, so what here should be
0.
Okay. So because we have assumed that the force is here. Okay. So in real transformers, it cannot be 0 because there is still a core because when here is the voltage. But however, we assume that the core is here, so here is only one that is in ideal situations, right? The ideal situations. So the ratio of the orange is the active ratio of these two terms. Okay, so it should be 0. Okay. So for the opposite voltage, so we will apply the rated voltage so that the V1 is here, but here V1 is not equal to 0. Okay. Secondary open. Okay, so we will measure the primary current and losses. Okay, and for the second test, the short circuit test, it doesn't connect these 2 points, so the I2 is no longer equal to 0. Okay, so there is a orange, so this is also a orange. Okay. That we also apply the voltage. Okay, so here we were just to apply a very lower voltage here because here is the short circuit. We use that to repeat voltage. The current here will be large enough. The current here will also be large so that this part of the transformer might be burned. Okay, so we'll apply let's say the norm voltage to the primary side and the rated primary current is low because there is a current, okay? So there is also the current here and the current here, okay? And then we will measure the voltage and the losses. Okay? So by doing these two tapes of the test, we can get the parameters in this equivalent circuit. Okay, so there's the examples. And so the amp meter voltage and angle. So this is the watt, okay? So it's the power. 100 megawatt and 200 versus 80 kilowatt. So the joule and half to 1, okay? Because 200 divided by 80. So in the following test, in the open circuit, we connect this, okay? We connect this to the 20 amperes here in the current and with 10 kilowatt losses. And when we short the current, we short this circuit, okay? So we say that the voltage should be voltage will be the 30 kilowatt and with another maybe 4 or 5 times more losses, okay, compared with the open circuit. So we should do calculate these 4 parameters. Okay. Okay, so in the first step, we're doing the short circuit test. So SC means the source, okay?
Short circuit current.
Yeah, for the short circuit, yeah, we touch this, okay? But however, here, the power, the current will flow here, okay? So here is, you can see that 100 milliwatt, and for this current, the voltage here is to be the 200 kilowatt, okay, kilowatt, and so the current of the source will be 500 amperes, okay, because in the primary side, the current is here low, okay. And for this, and what is this? Impedance of the transmission line, okay? So in transmission line, so although that the windings here is no current, but the impedance, there is a current here, okay? So the I source, no matter whether there is a current, the I source it will flow through this impedance of this transmission line, okay? So that here is a 500 amperes, okay? 500 amperes, and we can see that in the open circuit should be 10 kilowatt losses, okay? 10 kilowatt losses. So that reduces on the short circuit. So in a short circuit, we're doing this, okay? So it's 30 kilowatt here. Because we see that a short circuit, we're need to measure the voltage of each part and the losses, okay? So the voltage is 30 kilowatt, and this is current losses. between the 60 ohm. Okay, so these two, the sum of these two. So that the power, or we're gonna see the active power or real power of this and here is the reactance, okay? So here is the resistance. So you see that this here is a kilowatt. Here is not the kilowatt, okay? So here is not the kilowatt. You can see maybe you will have to you have matched this in your homework in sometimes, so that here is real power, okay? So real power is generated by the resistance. Okay, so this power is
Imaginary power.
imaginary side, imaginary side. Okay, so here's the real part.
Imaginary power.
So that the whole losses, because here is the real power losses, is produced by this. Okay. Because you can see in the short circuit, here is the power flow, here is the power flow, right? So we can see here for the real power of the source should be 500 kilowatt, so we can get this resistance of the transmission, okay? 2 ohm. That's more, okay? So that is the reactance of the transmission. You can use this triangle, okay? The triangle 60 ohm and 2 ohm. This is the approximate, okay? So it will not be equal, it should be approximate 60 ohm, because the 2 ohm is quite small, okay? So you see the large part of the impedance of the transmission lines to be the imaginary part. And for the open circuit, we will have the 10 kilowatt losses and 20 amperes. So in this case, we need to use some approximation, okay? So for the RC, because there's the open circuit, there's no current, so every current should flow through this, okay? In the short circuit, there is the current, because the impedance of the core is very large. You can see we assume that the current will flow here. So that in open circuit, no current, the current will flow through here. Okay. So that we assume that the rated power is actually will apply in both here and here. But in our real world, we will know that the impedance of the core will be much larger than the transmission lines, okay? From our previous consequences, we can see that the total impedance is 60 ohm, right? It's quite small. So that we will assume that the OR with power is applied here. Or with power is applied here. No voltage is here, okay? So it's approximation. So there will be 200 divided by the losses. Because the losses were also vary the most part of the 10 kilowatt losses is conducted by the resistance of the core. Okay, you could say that the RC Pretty note here is a parallel connection, okay? So the current will flow in here, okay? Flow at two sides, but we all know that the real power losses, so real power is produced by this, okay? And here is a 20 volt in the parallel, okay? That's why we call the RC, the resistance of the RC, the resistance of the core is can be calculated approximately 4 meter. So, okay, not larger, okay. Meter 4 million, oh, okay. Okay, and for doing this, so the other 3 parts, okay, so because here is the 4 parts, okay. So for the other 3 parts, we can also use this approximation, okay. Because you can see that in this part, the XM were not as large as the resistance, so that we will use them, calculate them together. Okay. So this one is due, so we are adding them all together. That the rated power, rated voltage divided by the current. Okay. So the current like this, the current like this is 20. So that sum of these 3 are the 10,000 ohm, okay? That because this part is only 60, so that it's actually, this one should be maybe approximately 10,000, okay? So it should be approximate. Okay, so in this examples, so we are using the approximate value several times, but this is not the key point, okay? So all you need to know is that short piece connected, there is a current, and we are seeing the current, all the current flow here. And for the open circuit test part, no current, all the power flow from here. And also, this part, the impedance of the core is generally larger than the transmission line, so that the voltage or current voltage can be applied. We can apply all the voltage here. Okay. So any questions here? No? Okay. So here is
residential distribution.
actually the real transformer in our real world, how it will work, okay? So because we are validating, so there will be potential distribution transformers. So we are generally use the single phase transformers. So, but however, so the most distributed system are 4 wells, okay? Phase A, phase B, and phase 3. And here is neutral, okay? So the grounding, yeah, grounding for C. Common neutral, okay, so will be this 3 phases. You can see there is only 1 phases. Here is only 1 phase, phase C, and here is the neutral phase. Here. Okay, so there is a American voltage level, so in China there will be the 1 and 10, okay. So it will be our home or campus. There will be a transformer on the primary side. Per unit calculation, okay? know that there will be so many range of levels in the power systems. So there will be a very big, the very important problem here is a large number of the transformers, okay? So because there will be so many levels, so that we will have difficulties, several difficulties to refer the impedance, right? Thus, impedance and voltage and power range, we need to transfer it from one side to another side, and then this side to the third side and to the fourth side, okay? So there will be very difficult to calculate in the power systems, which contains so many transformers, okay? So what we do is normalization, okay? So normalization, so everything in one standard, okay? Normalization of the all variables. So in the power systems, we call it the per unit, okay? So sorry, one moment. The per normalization, the per unit. So the quantity in the per unit will be the actual quantity. The quantity can be the impedance, can be the power range, can be the voltage, everything, or even the power, or either the complex power can be the quantity, actual quantity, divided by the base value. So in the per unit analysis, the most important part is the base values here, okay? Okay, so let's say that for the first scenario for the single phase system, okay? So for the single phase, the first one is that we need to choose one single phase. The VA is the watt, okay? The power base of the system. So what is S? S. So B, the subtitle B is the base. So what is the S here, uppercase?
Power.
Yes, complex power, okay? So we still remember because the complex power is correct, probably used in the per unit analysis, okay? So that the second step, we need to pick a voltage base. To pick a voltage base for each range voltage level, okay? So VE, the voltage level base. So the voltage base is related by the transformer turns ratios, okay? And in the per unit system, we will assume that the voltage here is refers to the line to neutral, okay? The net to neutral voltage, rather than it's the load, the line to line voltage, okay? So the third step is that we need to get the impedance base, okay? Because we know the power base, the complex power base, the voltage power base. Complex power base is equal to V. One part is the conjugate current. Anyway, so one voltage is bigger, and so the voltage divided by the conjugate current, okay? So it will be the impedance. So the third step is the current base, okay? So current is equal to the voltage divided by the impedance, okay? For the final, convert the actual power to the per unit. We just use the actual power to divide by different phase. Okay, so we have the power, we have the impedance, we have the current, we have the voltage. The four types will be how many four types of the quantities. Okay, so here is the one thing important that the per unit conversion will just to only to transfer the magnitude, okay? The voltage magnitude, the current magnitude. So there will be nothing to do with the angles. The angles, when you just to push your actual values to the per unit, and then you push back, you transfer back the per unit power, you per unit quantity to the actual values. Then there will be the same angle, okay? The angles is calculated separately, there will be nothing to do with this per unit. Okay, so the second one is that per unit quantities will no longer have the units, okay? That's like 1 PU. Here is, okay, so P on P dot U dot, here is the expression of the per unit. However, it's actually the voltage is 1 per unit. Is 1, okay, so this is not a unit, not the per unit volt, and here is just the expression of the per unit, okay. So in the per unit system, everything will have no units anymore, okay. So that procedures. So the first thing is that we convert everything. We convert every quantities, the actual values to the per unit, and we solve the problems or questions, and then we get the answers, we get the consequences, we transfer back to the actual values. Okay, so here's the one examples. So we need to calculate so many quantities. We need to calculate the current, the node voltage, the node power in this circuit, okay? Per unit methods with, and here in this system, we will assume that the base of the complex power is 100 meter watt, okay? So the voltage base is 10H kilowatt, 18 kilowatt, and 16 kilowatt, okay? So this is the actual value. No, this is the actual value, but we will use it as a base, okay? So that, for example, if we have this primary side, okay? So if we have the 2 PU per unit, so what is the actual value? Will be the voltage 2 PU, and so the H kilowatt is the base. How much? How many? What's the value? How much the voltage will be? Yeah, you understand? 2 PU. So H kilowatt is the voltage basis watt. So this is 1 per unit. So what is the about 2? Yes, perfect. You can just view the per unit. That's just 2 per unit. It means 2 bases. 3 per unit is the 3 bases. That's like for 3 PU. For here is 24 kilowatt. For here is 240 So the 40 kilowatt, and for here, the 40H, right? 40H kilowatt. So the SAM per unit, so you can say that because here is a different voltage level, right? But we have the only one per unit value because the 3, we can use the 3 to use the per unit value to express the 3 different voltage levels. So that's why we to do the per unit analysis, so it will be much more convenient. Okay. Okay, so let's conclude this actual quantities. Okay, so here is the H 0 degree kilowatt. Okay, so because it's 80, so it will be 1 to 10 and it is 15. So the 80, 5 to 1. And here the markings 1J. Okay, and the markings 24J. And here the markings 1J, but here at the node, maybe the node 10 ohm. Okay, maybe the resistor, inductor. Okay. Okay, so let's get started. Per unit. It's quite easy, right? For the Z base, you do it here, remember? So V is V square divided by the complex power, okay? Because we know that here is the V base, voltage base, and we also know that it is a power base, okay? So that we can get the impedance base, okay? Left, middle, right, okay? So the base for here, 0.64, the base for the middle part, 64, and for the third part, 2.56 ohm, okay? So there is the per unit, the basis. So in that case, because we know that everything will share one system, one unit, so that the ratio you will still be the 1 to 1, 1 to 1, okay? So we add them together. Okay? So anybody knows why here should be 1.56? Yeah. Why this?
This bold column, sir.
No. The original value is 1J, okay? So why here should where it's turned to the 1.56? Okay, yeah, right. How to calculate this? Okay, so you can see that the original value is H, okay? H kilowatt. Right here is 1 PU. Why is 1? Because the base is H kilowatt, right? So H kilowatt divided by H kilowatt, 1. And what is this? Do the same thing, okay? 1 divided by 0.64 here, right? And for this,
24 over 66.
yes, perfect. And what is this?
1 over 2.56.
So nominal for the node, so it should be 10, okay? Because the 10 ohm resistor is here in the third part, in the third side, okay? So it's B10 divided by this, okay? So that here will be the per unit value. You can see that because the base is 2.56, okay? And the per unit value is 3.91, okay? So that we can just to refer it as we have 3.91 per unit, okay? 3.91 multiplied with the base is 2.56, and we will get the actual value. So that you can see that the same circuit right in the three sides, we will just do everything in a single phase by the per unit system, okay? For this, the orange, red. How about this?
This addition of the
Sum up, okay?
0.56
Sum up, we can say the 3.91 here, and for this, we add them up, okay? And we can get this value. Okay, say, and we state previous, nothing to do with the angle, so it's a PU, not the angles, okay? So this, so also, although there is the angle, but this is still the per unit value, okay? So the VL is the voltage of the node, okay? 1 is the source voltage, and here is the current, okay? How about here? Where should the 1 minus this part? How this variables come from? Anybody knows?
the current divided law. This is the voltage divided law.
The voltage is the source, okay? So the voltage, so this 4 is the same voltage with the voltage source, right? We need to get this so that we need to, the voltage here is the source voltage minus the voltage in this recharge, right? The current is the same current, okay? The current through this 4 component, the same current, right? So how about this? X is 3 up, and Y 90 degree. Yeah, J, right? J is 90 degree. So this constant, so that we can get the voltage of the node here. Okay, it's here. Remember, it's a per unit, it's not the voltage. And for the complex power here, complex power of node, voltage multiplied with conjugate, okay, is equal to the voltage square multiplied with this Z, right? Like this, okay. Z is here, okay. Is here, okay. So for the source of generator, generator is voltage is here, okay. Current, because there is a serial connection, the current is here. So we get this. So the per unit of the everything we are getting. Okay, so any questions?
Yes, no.
Okay, so please wait.
I'll
Okay, so
and home is lovely.
If the
Combination
conjugate matters and
plus
yeah, just to convert, right? You know, conjugate is because it's a matters, okay? So it is orange.
same angle this plus.
What is this, sir? It's line sign?
Uh-huh. But here is the definition of the complementary power. You remember? So the voltage multiplied with the conjugate.
And what is wrong?
Yeah, in the previous, you could just to say the natures, okay?
That's almost zero.
Don't worry about it. Here, okay, so you do not need to do this, just say this, okay? So the square, that's V.
So direct b square দিয়ে গেল না তাহলে তো সেম রেজাল্ট হবে
Yeah. A conjugate is the different angle of the same magnitude.
নেগেটিভ
So that you do not use this. So the conjugate matters. Refer to positive. This one, but first with this one. You see the minus 30.8 degree. The positive speed 30 degree. 0 degree. Okay.
Okay.
Okay, so then we convert back to the actual values. Okay, we got to multiply the per unit values by their base. Okay, actual. This is the per unit value, right? Per unit value. Voltage of the current, the per unit. This is the per unit value. And this is the per unit, right? Per unit value multiplied with this power base. Okay? Because it is 13 kilowatt. 15 kilowatt, right? Is in the third set. Okay, so the S, the system power, base 100. The generator base also 100. Okay, so the current, the actual is the actual power divided by this. Actual voltage is here, and this is the base of the meter size of the power, and this is the actual. Okay, so this is the base. One part of it is per unit value, something like this. Okay, so we have a break. Okay.